So the recording is on now. Good morning or good afternoon, everyone, depending on your time zone. I'm Ryan Felton, a NASA postdoctoral management fellow from the Exobiology branch at NASA Ames. And I'm happy to have you here for our very first Artificial Intelligence and Machine Learning seminar series. The goal of this series is to improve the understanding and capabilities of the community when it comes to AI ML. And so the series will be fairly diverse. In some talks, we'll get into the weeds regarding AI, ML tools, and at other times take a step back and look at the fundamentals of AI, ML, and even pivot into mission capabilities occasionally. So today, I'd like to introduce Sam Gharib-Nezad from the Planetary Systems branch here at Ames. Sam will be discussing his work on using convolutional neural networks to predict brown dwarf atmospheric parameters and walking us through some of his code notebooks. So Sam, please share your screen and take it away.
Sure. Thank you, Ryan. Okay, it's here. Okay, do you see full mode now?
Yes, it looks perfect.
Okay, great. Thank you, Ryan. Thank you for the invitation, and I'm so excited to introduce the work that we have spent over the past 1.5 years. First of all, it's a big thanks to all people in the team. I made sure to have their picture here because I wanted to make sure, think about all the era that we are, the machine learning, AI era in which we have every day new models, new ideas with the GPT. Everyone is excited, and who knows, probably in a few decades, in addition to having people picture, I will have artificial intelligence somewhere there as a collaborator in the team. So I put this here to make sure that at least at the moment I acknowledge them and acknowledge people are doing these kind of works. And it's interesting. Look at the amount of data that we are getting every day. It's think about all the missions, either ground-based, either space-based telescopes, with all these data that we get every day. We have data, we have high-end and high resolution. James Webb has changing many things. We have information, image, spectra from different instruments with different resolution, and that require a huge amount of expertise and time to analyze the data. And the data are not only in one spectral regime. You can see, for example, this is the beautiful picture that's in our history, that in the left side we have from data, the image from HSD, and the right hand panel, it's from James Webb. And you can see we have data on different regime in UVBs, in infrared, and that require a lot of expertise. We need models. We need models, and we need to train the machine to understand and answer key science questions about the atmospheric dynamics of these brown dwarfs, about exoplanet, what is going on in terms of the climate, and the GCM models, which they are heavily time consuming, about the chemical composition, about the thermal structure, what is the TP profile, temperature, pressure profile, and how these exoplanets are different with our solar system. Do we have Earth-like planets? How to to detect and understand them, and also what is the synergy between these exoplanet and brown dwarf, if there is a formation of clouds, if yes, what kind of clouds do we have? A part of these questions, a part of this data or the intuition come from laboratory measurement, like we simulate these atmospheres and we get the data, and a part of that it comes from observation and a part is from modeling. And so now, I mean, think about all these information and think about what we want. I mean, when we ask a question about like all these information, we want to put it in context and think about Silicon Valley and think about like the last year. It has been full of announcement from all these big tech, biotech companies, and it was about GPT, it was about LLM, it was about these all models that have been implemented either in I don't know, oncology and about like, so we are in an era, we are in an important, like we are in a year or in a decade that we are using artificial intelligence and machine learning to help us with analyzing our data. And that comes from our passion, and it comes probably from our greed to more and more understand and decipher, to detect planets, to understand, to characterize, to detect them. And the idea behind, for example, deep learning is that you have cat and you have dog, and what you do is you train your computer. It's not, I mean, it's not it's not magic. What is going on is that you use a statistic, you use regression or classification, but the thing is that the model that you're using is very sophisticated. I mean, you use more and more operators, you use convolution layers, you use all these things. And think about think about facial recognition. For example, in your computer, you use like Face ID or things like that in your mobile. And what is happening is that it takes a part of your face and it trains the model. And as a result, it tells you if you are or not, or if it's cat or dog. And what we did, we use uh, so one step in interpreting telescope data is to take synthetic data, and in the second half of today, like seminar, I will talk in the notebook number 1, I will talk about the details behind it. But people, what they do, they generate different scenarios. They say, okay, we are detecting, think about this exoplanet, think about this brown dwarf. It has like all these different, like a range of temperature, gravity. And so let's think about all these scenarios and create thermal emission. And with this emission spectra, there is like a different ways, different scenarios for different range. For example, wavelength of 0.9 to 2.5. This is the flux that we expect, for example, on top left for the effective temperature. And this is what we expect. And then they use, I mean, the radiative transfer modeling. They use like forward modeling or retrieval, etc., to compare basically the model, these fluxes with the observation. And then say, for example, in 1.4 micron, for example, we have water because we have this absorption line and etc. Or 3.3 micron, we have methane, or there is water because of blah, blah, blah. So there is a lot going on. And this is what we are doing as a part of training these models. And today what I'm explaining is motivated by the two works, the papers that we are working on. Sorry. And and a little bit about the structure. So similar to what I showed you about the cat, either cat or dog, what we are doing with the convolution, and the name is CNN, not to confuse it with the news agency. It's convolutional network, and it's a part of deep learning. And with deep learning, it's a powerful method to train a set of models, and it has four components. You feed the model with the fluxes, with the synthetic data set. It cut them to different chunks, to different segments, and then feed them to the convolution. What happened in the convolution, it takes all those spectra, take a chunk of that and learn what is the pattern. In our world, like in other words, it learn the spectral features and then pass it to fully connected layers. And this is what it's called like neurons and the units, like analogy to our body, the neuron systems. And some of them are on, some of them are off, turn on and off. And it gets the training or the learning happen in this area. And then the last layer, it would be prediction. There is a lot of details going on, like how to avoid overfitting and all that things is something um, that we can discuss later. But just in general, we train the model and that's the output. And then there it comes with the performance, and the performance is it's how to gauge, how to assess the accuracy and the robustness of the model. And what will happen in notebook number 3, in the second half, I will talk to you about what we did. We split it in train and test set, and we trained the model on the data set. It's about 30,000 spectra. We trained 80% of we took 80% of the data set, the spectra, and trained the model, and then test it. And we use like R-square and few other regression metrics. But that's a part of showing the impact. The other thing that we did is developing this package. It's called Telescope ML. And it's under review, the package itself in Journal of Open Source Software. The package has 4 main components, modules. The first part is data master module, which it takes your data or this data set and prepare them, process them. The second step is deep trainer, which it do all the train the model. It takes the hyperparameters, all the parameters for the like how many layers in the convolution, in the fully connected layer, and it uh, do the training, perform the training part. The prediction is when you don't care about the training and you take our trained models and you want to do the prediction, and then the prediction is correlated with the other module. It's called StatVis Analyzer, which is it do the statistic, the visualization, and the analysis. Basically, what it provide you is with the statistical report and with the visualization to give you insights about what is not only the prediction from the trained ML models, but also what is the uncertainty, because we want to provide a full picture of the model performance and also the result. And you can see, not in addition to this package, we develop an online tutorial. Um, and in this tutorial also I had two interns which I mentioned their name, Ruchi and Gopal, which they also provided some tutorials about how to use GitHub, how to contribute it, how to do step-by-step to install the model, what is the structure that you see here, what is the structure of the code, and also the GitHub itself, which is fully open source. And this is what we believe on. We believe that we have two group of users. We have astronomers, which necessarily they don't interested in developing the machine learning part, but they want to use it. So we have documentation, we have installation, and we have tutorials there to help you to utilize those trained models without bothering with training. But also, if you are interested in training the model on your own data, then there is modules, the deep trainer and also the deep tuner, which we developed to help you with that. But also, if you are a data scientist and you just, enjoy looking at the darkest sky and thinking about exoplanets and brown dwarfs, and stars, but you don't care that much about. What you do is to add more layers, to add more sophistication to the machine learning part. For example, to think about adding noise, to use like, I don't know, instead of like I am using TensorFlow, using PyTorch instead, or I don't know, using different tuners. All that things is also possible with this open source project. And if you see in the name of the people of contributors here, and also it's not complete, like we have different people, different group. We have astronomers, we have data scientists. We trained a model and we applied it to a brown dwarf as a benchmark. And the one that we choose 313 brown dwarf, late type brown dwarfs. And late type, it's the temperatures um, between 600 to 900, 1,000. And the one that I'm going to show you now, it's HD 3651b. It's the first directly imaged brown dwarf companion to an exoplanet host star. And the exoplanet has the distance, I think it's about 0.2 AU, and also it's a Saturn. It's about a Saturn. It has a Saturn like mass, and so we did the prediction, and this is in the third. This is in the second notebook. I will talk about this. I'll show you this how to predict it, but. This is the prediction versus the observational data. With the observational data, you see the dots here. Those are the observation with their uncertainty. And this is from point about 8 up to 2.5. We train after training the CNN models, then we feed the model with the observational spectrum. The only thing is that we train the model, and that's the trick or the thing that I like. We train the model on a low resolution. Like what if you count the point here, the dots here, there are about 500, but we train the model on a lower resolution, on 1/5 of these, about on 104 points. And we wanted to see how it's the performance of the model. And you can see here the red is the predicted versus the observation. There are some areas, for example, about 1.25. You see there is difference here, or about 2. 2.1, yeah, you can see some differences. But other than that, I mean, the chi-square, the reduced chi-square is about 41, which that's another thing we discuss in the paper, if this is like a good metric. But you need more information other than just looking at at these benchmark and comparison. And this is what we did. So this is something that also I will talk about in more details in notebook too, but you see the temperature predicted about 765 plus minus 33, and the log G here, and the C/O ratio and the metallicity. This is the four target or four parameters that we train the CNN, the deep learning model on. And if I want to compare it with the literature, you can see there is like different prediction. And the prediction here, for example, for temperature, you can think about, I mean, you can see it's from 700 up to 850, and also the log G, the C/O ratio. In some cases, it kept constant, but in our case, we use multi-output regression, which it simultaneously train it on all model. And it comes from different methods, either forward modeling, retrieval, and different grid model, which it means synthetic data, and also some of them have cloud, some of them they don't have cloud. So I don't want to torture you by showing you this all details. So let's just show you a plot. And in the plot, if you look at this study, this is only in log G versus effective temperature space. And this study, which is the star, you can compare it with the retrieval work that has been done by Mike Lyon and Samland in 2017, and also with Zhizhang or ZJ in 2021. So you can see the overlap between them. And the temperature, I would say, is in line. It's in a very good agreement. Is in 1 sigma. The log G compared to ZJ to Zhang 21 is in line, the temperature, but the gravity is a little bit far in 2 sigma or even higher. So what I want to say is there is some challenges, and also in the paper, which it's about to submit in AppJ, we are discussing about what is happening on the behind it, like, because the clouds, the grid model, the equilibrium versus non-equilibrium is something that I also talk about in notebook one. But I mean, this is my last slide. And what I want to say is that what we are looking as we are moving forward, this is a big project, and this is started 2 years ago, and we are working all together. We have people like Hamid Migol from CoTI. We have Natasha, me and Ben Lu in Code S. And beside, we have interns, we have collaboration. For example, currently I'm working with someone who is very interested developing and adding XAI, and that is a very important module, and that's something that like big tech like IBM are investing on to understand this is explainable AI to explain what is going on, which features, which absorbers are responsible. And that will help and guide future missions like HWO and others like Raman. Or, I mean, we are moving forward to using high resolution for James Webb rather than using low resolution, and investigating different grid model. What if we add clouds? What we investigate this in different wavelength, and also what is applicable. Is it applicable to exoplanets? And we are currently, Natasha and I are collaborating with a team in Johns Hopkins University, and the idea is to develop this and making it applicable to exoplanet. Hypertuning, that's another thing which my colleague Miguel which is here also. He helped a lot in understanding what is going on with the hyperparameter tuning, what parameter we should use, and also having a platform that people, without installing it, they can use it. That's something that I'm expecting an intern from Georgia Tech University coming this fall to work with me full time and adding this feature. The open science culture is something that we are promoting, and I welcome everyone from everywhere with any level of expertise to contribute. That's the idea and the beauty of having this GitHub and open source. And AI ML Hub is something that Ryan Felton and Caleb Scharf are doing, like helping with having a hub, or like it's very critical. With that, I appreciate. Thank you for hearing my talk, and the next few minutes, if you have question, feel free to ask. Otherwise, I will start in the second half to discuss the procedure and the pipeline that we develop in our team. Thank you so much, and I would be happy to answer any question.
Thanks, Ehsan. So actually, I'm going to say let's move, unless there's a real specific question, I suggest we move to the notebook section. And so this is now the time where if you downloaded Ehsan's material beforehand or started it, you can follow along. If not, that's okay. You can follow along directly from what Ehsan will be guiding you through. But if you have questions or anything, this is a perfect time. Just raise your hand while Ehsan is going through the models. If you have a question, just raise your hand and I'll call on you and ask it, or you can ask anything in the chat. Don't worry about the question. If it's like, seems like a stupid question, just ask it. And we'll go from there. Rich, go ahead real quick. Rich, did you have a question?
Excuse me, I have to unmute myself. This question may not be too appropriate because it may require too long an answer, but I was looking at a recent paper that used machine learning to try to predict line widths of many different kinds of molecules. And my general impression of the paper is if someone, I mean, I'm not an expert in this either, but I know a little about it. I mean, I'm interested in it and I know a little about it. But if someone reading that paper who knew nothing about it would look at that kind of paper and say, well, what does this really mean? I mean, basically what they got, they made predictions and the predictions look quite reasonable. That is, they predicted line widths for species for which there were few or no measurements. Now, their predictions look very reasonable. But at the same time, you could argue, well, these are the same kind of predictions you would make if you looked at all the data and said, well, what does all the data tell me? And it looks something like this. And, you know, so maybe for the future, you know, trying to come up with metrics that convince people that, yes, this is better than just what you could do looking at the data yourself and making a reasonable prediction?
Thank you, Richard, for the question. This is a great question and a big concern. That's why we are thinking about XAI. So there is two things. What the method that you're seeing here, it falls in deep learning. The method that you are referring to for ExoMol, they have used traditional machine learning. With traditional machine learning, it falls in like ensemble methods like random forest, if you have heard, or just linear regression or things like that. With those traditional models, depending of course on the model, it is more easier to explain about the feature importance, about like what is the contribution of each, like the quantum numbers, the other parts of the input data. But with a metric, we have used different metrics, and in Jupyter Notebook number 4, I think, yeah, I will give you more details about what metrics we use to make sure that we are following. So yeah, basically there is like different metrics, different measures that we check to make sure that the answer is understandable and interpretable and trustable, of course.
Okay, thanks. Yeah, no, I mean,
Thank you.
yeah, because I know it's a complicated topic. And I remember that their paper, the ExoMol paper, they talk about machine learning specifically. And then they have about 5 different methods they tried, I think, something like that. Yeah.
Yeah, I mean, with this method, that's another thing. I will explain instead, I think in notebook number 4, about like what challenges or what items, what critical items we considered when we trained these models. So, okay, great. Shall we go to the next half of the hour?
Yeah, this is perfect.
Okay, great. So in the next hour, we have about half an hour, and I'm going to discuss with you 4 notebooks that I posted and publicly available that you can use to you can implement those models, train models, to do the prediction on your data set, or you can train the model, new model, CNN model on your data set and do the prediction, right? So, and also I will talk about 4 notebooks. I will walk you through and also feel free to stop me and ask question. You don't have to, I mean, wait, this is not talk, the next half. So, okay, the first step, the first tutorial. So the first tutorial is about EDA, exploratory data analysis. It's exploring the brown dwarf synthetic data set. A little bit about the data set that we use. The data set that we use. It is called Sonora Bobcat. It's from Mark Marley, published 2021. And so with these model grids, basically the way that they create these models, they simulate or they create these atmospheres in a machine. And what they do, they have the object in a very simple word, of course. They add the chemistry, they add physics, they add convection, depending if it is non-equilibrium or they just want to stick to equilibrium, they add opacity, they add the chemistry, they add all the processes, the interactions, and at the end, what they get is something like this, which is what you see. It's entangled. What you see here is very complicated, and it has gravity, it has effective temperature, it has luminosity, which is the red lines here, like how much luminous. It has the mass of the object, which is, this is brown dwarf. So it's from from half Jupiter mass up to, I think, 82 or 85 Jupiter mass. It has the age of the object, and this is all about part of the beauty and complexity of these models. And at the end, what you see is a spectral. So that's the goal. I mean, when you hear about interpretation, that means what we need is different spectral. Like we need model grid that generate TP, temperature pressure profile. And then with the temperature pressure profile, for example, in my work, I use Picasso, developed by Natasha Batalha, Dr. Natasha Batalha, and the result is this thermal emission. And with the thermal emission, this is for different scenarios. For example, what you see here, for example, from 1 to 1.15 micron, you have FEH. You have in 1400. If you think about, let's say, 1200 Kelvin. In 1200 Kelvin, from 0.9 to 1.1, we have sodium and potassium. And also in 1.25, we have potassium lines. As we go down in the temperature, like lower temperature, you have methane will be more dominant, and you have ammonia. So there is a lot of like information there, and that's the first step. That's the first notebook in this series. So what we are doing here, this notebook is walking you step by step, telling you how to. If you need, you can go to the, you can click on the installation link, and then download the reference data from Zenodo, follow these steps, and that's the first step. And then after installation from Telescope ML, you call StatViz Analyzer, this module, and then read the data set. So this is the part that you can change based on your training data set. So you're in your training data set directory, that is a part of the data structure, the training set. You will read the data here, which this is the wavelength in micron, from 2.5 micron up to 0.8. This is the metallicity C/O ratio, and this is coming from Sonora Bobcat grid model. And you do this analysis, I mean, just doing the visualization to see like what is the temperature you are expecting, what is the gravity, and there is some challenges, of course. For example, look at this one here, and I can show you, this is like the output that's from this notebook. For example, for C/O ratio, for like the bottom left side, for 800 Kelvin log G5, for any C/O ratio lower than 1, which 1 is the solar, they are very identical. And that was one challenge we had when we trained the CNN model, because the model can't, I mean, get confused. But so that's something that you should consider. And so that's done with notebook number 1. Any question we have here? Okay, so if there is no question, then we can go to the next step. So next step, it's a little bit, so it's showing the workflow of the prediction. And in the workflow, what we did is, this is prediction, like assumption is that you don't care about training the model. Use our trained model, and all you do is just like doing the prediction and extracting these parameters, temperature, etc. There is step number 1, preparing the synthetic fluxes. You do that, and this is a part of what we did in the back end. The second part, which this is something that you need to do, is to prepare your observational flux. If your flux is in lambda regime, in wave length, you should change it to nu f sub nu. And then another step is tuning the radius, because the radius is not, so the radius is a part of fitting a part of fitting the observational spectra. It's not a priori in the model, to the model. And that's true in forward modeling, and that's the same in CNN. In CNN, the data that we are providing and training the model is top of atmosphere. So we perform this training by looping over, tuning the radius by looping over a range of radius, and I'll show you in a second what will look like. But the idea is looping over the radius and then predicting the flux and generating the flux with ML, and based on the generated flux by machine learning by CNN, you calculate the chi-square between the predicted ML versus the observation, and you find the R in which you have the chi-square, the reduced chi-square minimize, and then use that to the next step to do the prediction. And before this, I can go over this step. So here from the model telescope ML, you need data master, you need the predictor, you need the StatViz analyzer. And again, you read the data, you do some processing, which I will talk to you in step number, in Jupyter Notebook number 3 and 4. Yeah, please go ahead. Yeah. Do you have a question? No? Okay. So when you tune the data, this is the data predicted. This is the parameters recently predicted. I mean, not recently, 2021, but by Zhang. And this is for this object, the temperature, etc. What we need here is, first of all, tuning the radius. And in the tuning the radius, we can start from any number. Like, let's say I start from the predicted previously 0.8, and then loop over this plus minus 0.4. Here, what I'm showing, just like for few cases, the one that I have for for the radius, I have 0.4, 0.41, 0.42. So I have it for many with like short, like narrow intervals for the radius. It goes from this number, and for each one, I have you can calculate the chi-square. You can ignore the p-value, but this comes from the idea that we can do hypothesis test as well. But I don't want to go in detail right now, unless you have questions. But you have the radius, you have the chi-square. For each chi-square, we generate by the trained CNN model. We predict the gravity, temperature, C2O ratio, and metallicity. And we generate the flux in each case. If you want to see the visualization,
I have a
that's another.
question. Can I just?
Yes, please.
Yeah,
absolutely.
if you can go back to the diagram that you had before showing, you know,
Sure.
just yeah, that one. Okay, so prepare. So I'm not very familiar with all this, but prepare the synthetic flux. What do you mean by, you know, you have observational flux. Let's say you are an observer. So you have observational flux. What is the synthetic flux?
So this model, so the prediction is based on synthetic data, right? And it doesn't matter, this is machine learning or this is forward modeling. What you do, you have synthetic data. The synthetic data comes at this point coming from Bobcat, from Sonora Bobcat model. And so the synthetic data is the training data set that we use to train the CNN model.
Okay. But why do you need, so when you say prepare it, so you have to, for your specific situation, is it done automatically, or how do you prepare it, given that it's something that, it's data that you already have, right? It's something that you train on. When you say prepare, what do you need to do?
So if you're an observer, you don't need to do anything. All you do is just going here from the beginning and reading this data set. If you want to use this model grid, and for example, this model grid doesn't account cloud. So account for cloud, it's cloudless. So if you're working with L-type dwarfs, you most probably have clouds because their temperature is about like 1400 Kelvin effective, their effective temperature. So this is not a right grid model for you, model grid. You need another. But if you are working, for example, with T dwarf, with Y dwarf, which temperature is lower than 700 Kelvin. In that case, you don't care about the training the model. You use the CNN models that we train for you or other group have trained using telescope ML. What you do is just loading the data set here that is trained, just like going over these cells. And then here on this step, you need to load your model. I mean, and the model that you're loading, I mean, the observation that you are loading here, here I'm using HD 3651B. But if you go to that data structure, there is also a directory for observational data set. At the moment, for example, I have 3 benchmarks, all late type brown dwarfs. You can have your own object here and load the model, load the data set, the observation, and then follow these steps again based on your object and tune the radius to find the best fit. And then, for example, here, the best fit is about 30. The radius is 1.1, and it gives you the chi-square equal 30 reduced chi-square over the data point. And then here, again, you load the data, your data, or just like this example. And then here there's like, this is like this observe parameter predictor. This is, you instantiate this class from predictor module in Telescope ML. And then you go over, this is example of observational spectra in F sublong. And then you go over these steps. Some of them is just like showing you like what is happening inside. You can totally turn them off. And then it creates the prediction. This is just for 10 loops. And what we are doing here, I see we have 10 minutes. So what we are doing here, we are looping over over this this observational spectra, and creating sampling, creating a sample of 10, or at this point for this paper, we create a sample of 1,000 within 1 sigma. And the reason is we not only want to understand the prediction, like the temperature, etc., but also we want to see what is the uncertainty in the temperature based on the uncertainty predicted by observation for these points, for these data sets. And here to give you an example, like for this object, this is for 1,000 loops, and this is what we are getting for the reduced chi-square. And we have 1,000 loop here. That means we have 1,000 of observation spectra within 1 sigma. We generated those, and each time we looped over C number 4, we looped over 1,000 sampled flux, and we predict the temperature. And this is the range of temperature, 765 plus minus 30. You see the distribution, and also you see these box plots, which it shows you the median, the medium, and also this like the 50% of the data and etc. And also you see the outliers as well. So this is the kind of information that you get from this output. So I see we have about 5 minutes. I can quickly show you the step number 3 and 4, which is from tutorial number 3 and 4. If you want, you can reach out to me later with more details. But for more questions, more discussion. So the tutorial number 3 that I have is processing the data set. If you want to apply this, like if you want to use this model on your, this like package on your own data set, then you should consider doing numbers 3, number 4, notebook number 3 and 4. And in this notebook number 3, you process the data set, you split them to train, validation, and test. You generate some features, engineer new features. In our example, we use mean and max for each, and also you scale them. In the scaling, also another thing we retained the correlation, the relation between the parts, each spectrum, the points between flux points between the spectrum by doing like row-wise instead of column-wise scaling. That's another thing we try to make sure that we follow. And as a result, we get this process this data. And after we processing this data, we use Bayesian statistic. It's called a package called BOHB, Bayesian Optimizer Hyperparameter Band, which is a statistical method to find and tune the hyperparameters. And the hyperparameters that I talk about, which this is tutorial number 4, it's think about the number of convolution layers, number of kernels that you need for each layer, how many layers do you want, how many block you need, and also this is fully connected component. What is the number of neurons that you need? What if you have uncertainty or overfitting, and also you concatenate it with the features that you engineer, and then there is another layer fully connected, and the output is temperature, log G. You can add to it. I mean, that's the beauty of open source. You can add, for example, what if we have cloud or no cloud? What if we have, I don't know, other parameters, what we have KZZ, and this is something that I'm currently working with one of my colleague Mahdi in Germany, and he's like, for example, adding XAI to explain, for example, which part of this flux is responsible or it's more has more impact on the output, because that will help, first of all, us as an astronomers to understand, and a spectroscopist to say, for example, water dominant feature in, I don't know, 1.4 micron is important here. It has more contribution, but also for future instruments, for future telescope, we can guide them. We can say, okay, this is the particular spectral region that we care about. It's important in our analysis and in understanding the composition of the atmosphere. And back to Alessandra's question, and also to Richard about, they said, like, the question was like, the question is that how we gauge the performance, how we assess the performance. We use MSE, mean square error, we use MAE, we use R square, we use mean residual, and you can see an example of the performance of the model itself, because we need the model to be robust, accurate, and be able to predict the test data. So we had like 80% as train and like 10% test, and we kept the test data set aside, the training, we train the model, and then we do the prediction. And you can see what is we use many metrics. For example, I use mean residual because I wanted to see if my model is biased or not. With that, I think I don't have anything else. I see we have few minutes. If Ryan has any announcement or if there is a question, I would love to answer. But feel free to reach out later. I know there's a lot of like information, and I don't expect you to follow like everything at the moment.